Welcome to section 2.5. We're talking about zeros of polynomials. I'm going to start off with just a couple of intro questions to make sure that we're back into the idea of factoring and setting things equal to 0, and then we'll move on from there. Let's start though with the first one. Find the degree and then find the zeros. The degree, don't forget, the degree is the exponent, highest exponent. In this case, the highest exponent is a 1, so my degree is 1. In order to find the zeros, I set my function equal to 0, and then I solve for x. In this case, then, x equals 7. So my 0 is 7. Okay. In part B, take a look, the degree is 2. That means we should have 2 solutions. If I set this equal to 0, you have 2 options for solving. You can either factor or quadratic formula. In this case, I'm going to factor because it's easier and it can be factorable. I know that 5 and 2 will somehow get me 3, but in order for it to be a negative 10, my 2 would have to be negative. Therefore, I have an x plus 5 and an x minus 2 equals 0. And if I set each grouping equal to 0, then what I end up getting is negative 5 for a 0 and positive 2. Okay. If you look at part C, in C there are only 2 portions of this, but you'll notice the degree is 3, which means I should get 3 solutions. But since I only have 2 terms, what I'm going to ask myself is there anything in common? And there is, and I'm going to pull out one x, because they have one x in common. If I pull out an x of the first one, I'm left with x squared and then plus 9. And I'm going to set these each equal to 0. And you'll see this first one gives me a 0 of 0. If I set the second one equal to 0, I cannot factor because of this plus. The sum of squares is not factorable, so I'm going to set this equal to 0 and I'm going to solve it. X squared is negative 9. Remember that when you square root, you get 2 answers, a plus and a minus. A negative underneath the square root means there's an I, and the square root of 9 is 3. So I have another 0 of 3i and a third 0 of negative 3i. Okay, so we're bringing the complex zeros back from section 2.4. The final one, you'll notice again the degree of this is 4, which means I'm looking for 4 solutions. Again, I only have 2 terms, which means I'm going to try and pull something out. I can take an x squared out, and then I'm left with x squared plus 4. And I'm going to set both pieces equal to 0. Okay, this first one, when I square root, I end up getting 2 answers. We just don't normally say a positive and a negative 0. That just kind of mathematically doesn't seem right. What this means though is my 0 happens twice, because I'd have that positive and negative, and really a positive and negative 0 is the same thing. And the way we write this is talking about a multiplicity. And so what we'll say is we have a 0 with a multiplicity of 2, and that means it happens twice. And this multiplicity is super important. When I solve my other one, it's really just like C. I get x squared is negative 4. When I square root, I get plus or minus 2i. So I have a 0 of 2i, and I have a 0 of negative 2i. And I like to separate them. And when you give it to me on a quiz, you don't have to. I like to separate it though, because I can see there are 2 zeros here, 1 0 here, 1 0 here. That makes a total of 4 zeros. And so I did the intro in this section just to make sure that we're okay with factoring, that we're okay with pulling things at greatest common factor out, and that we go back into the complex numbers for I. Okay? This fundamental theorem of algebra is huge, absolutely huge. What it says is a polynomial of degree n. So if a polynomial has n, the n exponent, then there are exactly n zeros. So like we saw above, in part A, the degree was 1, I had 1 0. In B, the degree was 2, we had 2 zeros, and so on and so forth. That includes that idea of a multiplicity. Let's get my pen working. Multiplicities. Okay, it includes multiplicities and using complex numbers. And so what it says, you'll notice really this is talking about part D. I guess it's not a number, it's a part. Part D. This is saying we have multiplicities, we have complex zeros that gave us the total of 4 zeros. And so that's kind of the idea for the fundamental theorem of algebra. I want to go back and talk about two definitions that you learned in middle school, but let's make sure we're set. A rational number is a number that can be written as a fraction. And I'm going to use the fraction p over q today. That's kind of the notation your book uses, so I'm going to stick with that. An irrational number cannot be written as a fraction. Irrational numbers are things like pi or e, something like that that doesn't have a really nice way of writing the fraction. And so this kind of gets us into some background knowledge, and then we'll do this rational test to find zeros. The reason we have this rational zero test, and basically what it's trying to do is find all of the possible zeros. We know our calculators can do a lot, but again, we're taking those away from you at some point. So I want you to get and see the idea of how would I do this without my calculator, and I'll show you that your calculator will simplify for you this chapter. But the way to find all of the possible zeros is to make a fraction p over a q. The values of p are the factors of the constant term. And the constant term is just basically that idea that you don't have a variable. Okay, so, you know, if there's a +4 at the end, you would list the factors of the 4. Q are the factors of the leading coefficient. And the leading coefficient is the number that's in front of your degree, highest degree term. So what we're going to do is we're going to set up a fraction, and we're going to basically look at all of these possibilities. Now this is true as long as P and Q don't have a common factor except 1. And so basically what this is saying is as long as we don't have something else in common, you know, like they're not both 1 and 4, you know, or there's a 4 in front and a 4 as the constant. They want to make sure that there are different possibilities. What it is going to do then is give us these possible rational. We're talking about fractional zeros. And so here's what I'm going to do. I'm going to show you the possible zeros for this polynomial. And so what we're going to do is we're going to do our p over q. So I'm going to start with my constant, and my constant in this case is 10. Okay, and so I'm listing the factors of 10. I could have 1, 2, 5, or 10. So 1 and 10, 2 and 5. The only problem is I could have the negative versions of that as well. I could do a -1 with a -10. And so what I'm going to do is put a positive and a negative in front of each of them. And what that'll do for me is it'll account for the fact that some of the times you can multiply them to be negative, 2 negatives, some of the times it might be 2 positive. And I'm going to divide it by the leading coefficient, which is 3. And so the only way to get 3 is to multiply 1 and 3, or -1 and -3. Okay? Now what we do, and I'm going to switch colors so you can kind of see this, what we're going to do is now divide these. So if I do 1 divided by 1, either in the positive or the negative version, I could get a positive or a -1. And if I did 2 divided by 1, I could get a positive or a -2. And 5 divided by 1 is a positive or a -5. And 10 divided by 1 is a positive or -10. And so this is the first thing. And I'm going to change my color again. Let's do the other one. I could take these divided by 3. So 1 divided by 3 is ± 1/3. And 2 divided by 3 is plus or minus 2/3. Let me get rid of this guy a second. And then 5 divided by 3, and I know this is getting a little messy, but plus or minus 5/3, and the last one plus or minus 10/3, when I could divide it this way. Now normally you won't show this mess over here, but you'll list out all of these possibilities. And so the idea is, if these are all of the possibles, could I actually find the true zeros? Well, let's talk about how they did this before calculators. Before anybody had a calculator, they would take this positive one and they would synthetic divide my original polynomial. And if that didn't get me a 0 at the end, then they'd go to -1. And if that didn't work, then they'd go to 2, and then they'd go to -2, and they'd have to test all of these zeros. Now, what's great for us is we have a calculator, so we don't have to do that, but I want you to do these possible zeros so that you can look on your calculator, and I can look in my table and say, does 1 or -1 get me a 0? Oh, they do, so I can go try it. Or does this get me a 0, yes or no? No. Okay, does 2/3 get me a 0, yes or no? No. And so you can kind of look at specific values in your calculator to kind of help you find what are the actual zeros. Okay, so here's what we're going to do. We're going to start in this next example by always listing the possible ones. Okay, so I'm taking my P over Q. My constant term is a 6, and again, I'm just going to include the plus or minus no matter what. So in order to get 6, I could do 1 and 6 or 2 and 3. So I have 1, 2, 3, and 6 on the top. The leading coefficient is just 1, and the only way to get 1 is 1 times 1, or -1 times -1. So really my possible zeros are positive or -1, positive or -2, positive or -3, and positive or -6. What I want you to do then is go to either your graph or your table for a moment and see if any of the positive or negatives are actually zeros. So you might want to pause the video a second and figure out of these 2, 4, 6, 8 zeros, how many of them can you see on your either graph or table as crossing the x-axis, or in your table as getting a y value of 0. Once you do that, then we'll actually go through and find the remaining ones. Okay, from your graph or your table, you should have been able to find that the zeros off your calculator are x equals -1 and x equals 2. And so once I know my actual zeros, I'm going to go back to section 2.4 or 2.3, and I'm going to actually look at this and say, okay, let me synthetic divide with -1. Well, I have my coefficients, 1, -1, 1, -3, -6. The goal should be to get a 0 at the end because you've told me those are zeros. So I drop the 1, -1 is -2, and 2 makes 3, and -3 makes -6, and a +6 makes 0. Okay, so that's a good thing, check. We want that to happen. I'm going to synthetic divide one more time with my 2, and again, I like to just continue it. This gets me a 1. 1 times 2 is 2, which gets me 0. 0 and 3. 3 times 2 is 6, which gets me a 0 at the end. Again, that's a good thing. So I'm left with this polynomial. Remember, remainder, number, x, and an x squared. So I have the polynomial x squared plus 3, and I want to find the remaining zeros. This really goes back to the intro. I can just subtract 3. X squared is -3. When I square root, I get a positive and a negative. I square root's a 3 because you can't square root the 3. So let's go back to this idea. My degree is 4. I should have 4 zeros. Well, 2 I got off my calculator. So I have a 0 of -1 and 2. And the other 2 came from solving. I square roots of 3. And negative I square roots of 3. Okay, and so you should find 4 zeros. Please keep in mind, I do want to see these possibles because that tells me, that gives us an indicator of where should we look on our calculators. Let's flip the page and try one more. let's go in this top example. We got to find our possibles. Okay, so in order to get 20 for my constant, I could have 1 and 20, 2 and 10, or 4 and 5. Okay, so there's all of my possibles. If you notice, my leading coefficient is 1. Could you divide this thing by 1? Yes, but truthfully, those are going to be our leading ones. So you go to your graph or your table, and from my calculator, I found 1, 0, x equals 2. Okay, this is the only 0 I found. So I'm going to take my 0, and I'm going to synthetic divide. 1, -4, 14, -20, and I better get a 0 at the end if it's a 0. So I drop the 1. 1 times 2 is 2, you get -2. -4 makes 10, and 20 makes 0. Again, this is my remainder, my number, my x, and my x squared. So I have this polynomial left, x squared minus 2x plus 10. And my goal is to find the remaining zeros. Okay, well, let's look at, if it's possible to factor, we want to factor. 10, the only way to get 10 is 5 and 2. 5 and 2 has no way of adding to get to 2, so I need to quadratic formula. A is 1, B is -2, C is 10. All right, here we go. 2 plus or minus the square root, -2 squared minus 4 times 1 times 10, all over 2 times 1. 2 plus or minus, you end up getting here 4 and -40 makes the square root of -36 all over 2. And we want to break this one down before we do anything. The square root of 36 is 6, and because there's a negative, that means I. So I'm going to move this up here. 2 plus or minus 6i all over 2. And now you can divide by 2. You get 1 plus or minus 3i. Okay, so if I go back up to my degree, I should have 3 solutions. Well, 1 I got from my calculator, so 2 is one of them. And the other 2 came from solving, so I have a 1 plus 3i, and I have a 1 minus 3i. Okay, so there are 3 zeros. I have one last example, and I don't want to do all of it, but I want to get you started, and then I'm going to have you do that in class. I want you to look again for possible zeros in the next example. In order to get 8, I could have 1 and 8 or 2 and 4. And again, the leading coefficient is 1, so I don't really need to divide those by 1. When you go to your calculator, you will find, most of you probably are using the table, you will find there are 2 zeros, at 1 and at -2. Okay, but I do want to talk about one thing. I want you not only to go to your table, but to also look at your graph. Because when you look at your graph, here's what you end up seeing. And I don't know the exact picture, but I want to give you this kind of idea. At -2, it goes through, and somehow it comes up. And at 1, what'll end up happening is it'll touch at 1 and leave. According to our idea of multiplicities, if it goes through, this just happens once. But if it touches and leaves, this happens an even amount of times, and we're going to assume twice unless I need 7 or 8 zeros. And so when you synthetic divide, you have to take this 1 and synthetic divide with it twice. There's my hint for you going through. What I would like you to do is do this before you come to class. Okay, because you need to make sure you're practicing. And again, I'm giving you at least the hint to look at the graph. This x equals -2 only happens once, but at 1 it happens twice, so synthetic divide twice. Okay. I'm going to keep going down then. Looking back at the last two examples, again, at least example on the top because we did that together. Complex zeros, anything with an I, always occur in conjugate pairs. Always occur in conjugate pairs. That means if you have an A plus BI, A minus BI will always occur as well. Truthfully, the same thing happens with square roots also. If I have a zero of a negative square root of 4, I don't want to do 4, 5, then a positive square root of 5 would also be a 0. And so keep that in mind. Square roots and complex numbers come in conjugate pairs. Our goal is to say if we have these zeros, then what we can do is write out the original polynomial. Well, if 2i is a 0, then negative 2i is also. Okay? And so I'm going to take these zeros and write them as factors. If 7 is a 0, x minus 7 is a factor. If 3 is a 0, x minus 3 is a factor. If 2i is a 0, x minus 2i is a factor. And if negative 2i is a 0, x plus 2i is a factor. And we want you to actually FOIL these out and figure out what happens. So I'm going to shorthand this just based on time. I'm going to multiply these two together, and you get x squared minus 10x plus 21. And I'm going to multiply the i's together so that i's cancel out, and you end up getting x squared plus 4. Okay? If you're not sure how you get these, take it along the side or something and do some work over here to figure out how to get those. Our last step then is to multiply these, and I'm going to do this again quickly. Here's what you end up getting, and so make sure you can do this. X to the 4th minus 10x cubed plus 25x squared minus 40x plus 84, and I'm going to equal that to f of x. This is my polynomial that would have those 4 zeros when I went to find them. And again, I should know that because I should end with an x to the 4th. I have 4 zeros, my polynomial should be an x to the 4th. Okay? So this is the idea. You will be required to do something like this on the quiz. I have one more example and I'm going to get you started. And then I want to actually finish this. Actually, you know what? No, I'm going to do this in class, because you're going to need a separate sheet of paper. What I want you to do, though, is to read the example like this in your book to kind of get the idea, but we will go through this one together in class. Okay? This one's more in depth, but I can tell you this is definitely a great quiz or test question. But I want to make sure that you have the time and that we can actually walk step by step through this. So thank you for watching section 2.5. And again, we will cover this one in class, and I also want you to do the one from above on your own. So we'll have a couple of things to discuss in class.